Okay. There is a problem initially. Now we'll start it. And in the earlier class, we have seen that there are para, ferro, and antiferromagnetic materials. And there is a temperature called Curie temperature for ferromagnetic materials. And below Curie temperature Tc, they are ferromagnetic. And above that, they are paramagnetic. And the antiferromagnetic materials also will have a Néel temperature Tn. Below Tn they are antiferromagnetic, and above Tn they are uh, paramagnetic substances. Now we will concentrate on ferromagnetic materials and their properties. As you have seen that ferromagnetic materials are generally used in magnetic materials like iron, cobalt, nickel, etc. Now, what are the properties of these ferromagnetic materials? They are showing very high susceptibility, and the materials are strongly magnetized in the direction of applied field. This is because, their property is that they have magnetic moments aligned in a particular direction, and therefore they are strongly magnetized. And they show magnetic domains. What are these magnetic domains and why they are strongly oriented dipole moments? We have to see it. Now, to understand these magnetic dipole moments, we have to see that I take a iron bar or iron material, something like this. And we have written in the ferromagnetic materials that they have magnetic moments of equal and parallel dipole moments like this. All of them are exactly oriented in the same direction. But it was observed that in a given material like iron, if all of them exactly oriented in the same direction, their spontaneous magnetization is so high. Therefore, even iron or cobalt or nickel should show magnetic properties and magnetism at room temperature also. But we have seen that iron is not magnet. It will not direct attract. It is a magnetic material, and it get magnetized in the influence of external field. But by itself, it is not a magnet at room temperature when there is no external field applied. This is what is the reason. The reason is that even though we say that the magnetic dipole moments are or spins are aligned in the same direction, it was observed that in the material of a ferromagnetic nature, the spins are, of course, they are parallel, arranged in the same direction, and but this parallel arrangement of spins or the magnetic dipole moments are only confined to a particular region. If you go to the next region within the material, again they are okay oriented in the parallel and same direction, but their alignment of the dipole moment is different from the previous region. And if I go for another region, something like this, in it the magnetic dipole are in this direction, but within that region they are aligned in the same direction, and they are also having same magnitude. If I go somewhere here, they may be something like this. That means in a ferromagnetic material, magnetic dipoles or spins are aligned in the same direction with the same amplitude, but limited to a small region. And this small region, we call it as a magnetic domain. So this is a magnetic domain if I take it, and this is another domain, this is another domain. Domain is nothing but a region in which magnetic dipoles are oriented in the same direction. But from region to region, if I go from one region to another region, you can see that the direction of alignment is different, and here the alignment is different. Therefore, the magnetization that is given by this domain will be cancelled by the magnetization to this. And similarly, all of these randomly distributed zones are called domains will cancel the net effect of magnetic moment, and thereby iron at the room temperature is not a magnet like nickel cobalt also. That means the magnetic zones along which or within which the dipoles are oriented in the same direction, the small regions are called domains. So therefore ferromagnetic materials show domains, and these domains, okay, when you see it, these domains are from one domain to another domain, the orientation is different. Therefore the net magnetic moment is zero for a material, and hence even though we call iron, nickel, cobalt or ferromagnetic materials showing spontaneous magnetization because of existence of domains, and these domains are randomly distributed, therefore they cancel each other, hence they don't show net magnetic effect. And these if you apply a magnetic field externally, what happens is that I have domains within it like this is one zone, another zone. In this zone all are oriented like this, in this zone all are oriented in this direction, and some other zone they are oriented like this when there is no external field H. But if I take the same magnetic material now, I'll say that I have domains, but I apply some external field H. Okay, here is H is equal to 0, so I keep H is equal to 0 in this case, first case, and therefore they are randomly distributed. In the second case, I apply some magnetic field in this direction. Therefore, these domains, within the domains, the magnetic dipole moments which are there already in the direction, they're exactly oriented in the direction of the applied field. But those magnetic domains which are in the other directions, they start orienting in the direction of applied field, and all of them will come to the same direction. Therefore net magnetization is more and not zero. So therefore when there is no magnetic field applied, the magnetic domains are randomly distributed. When external field is applied, the magnetic spins, or we say magnetic dipoles, start orienting themselves in the direction of applied field. As they are orienting, as they are rotating in the direction of applied field, the entire sample will have the net magnetization in the same direction of applied field for a ferromagnetic substance. Therefore, they show magnetism. Now, if you see the facts about ferromagnetic materials, these ferromagnetic materials will show some exchange forces. These exchange forces are quantum mechanical phenomena. Therefore, to understand ferromagnetism, we have to use quantum mechanics to understand the ferromagnetic behavior. Now, some of the examples of ferromagnetic materials are iron, nickel, cobalt, and some other alloys. But you should remember that a ferromagnetic material must show two distinct characteristics, and one is spontaneous magnetization. We defined spontaneous magnetization as a magnetization shown by a ferromagnetic material even in the absence of external magnetic field. That means the net dipole moment is not zero, but this net dipole moment is not zero within the domain only, but different domains may be aligning in different directions, and hence the total magnetization of the sample may be zero, but they show spontaneous magnetization and non-zero magnetization even in the absence of external magnetic field is called spontaneous magnetization. And in case of other important thing is that they show magnetic ordering. Magnetic ordering means that the dipoles are or magnetic dipoles are oriented in the same direction with equal amplitude or equal magnitude. Therefore, the basic characteristic of a ferromagnetic material is to have okay, equal and oriented in the same direction dipoles. That means the dipoles, whatever we are taking, will have same magnitude, but all of them are oriented in the same direction, like this. This is called magnetic ordering. This magnetic ordering will happen only below Curie temperature T less than Tc. So we have certain ordering which is called magnetic ordering, means the magnetic dipoles that are present in the domains are oriented in the same direction. These are the two basic characteristics. Now, how do we get these equal and say same magnitude dipole moments? The magnetic dipole moments arises from the atoms. These are the atoms, and this is the direction of the magnetic dipole moments created by that atom in the substance. The atoms are so arranged in the lattice that their magnetic moments are in the same direction. So therefore, it is the ordering of magnetic material, magnetic dipoles due to the lattice structure. The structure plays or crystal structure plays a very important role in magnetic materials. And how the neighboring atoms are having magnetic dipole moments is important. If the neighboring magnetic dipole moments are arranged in the crystal lattice so that they are parallel and equal in magnitude, then we'll get ferromagnetism. And if you see this, ferromagnetic material strongly attracts the external magnetic field lines of force into it. So they are going like this into it. Therefore, they have more lines going into the material. Okay. So now you see this structure. This is the unit cell of a ferromagnetic substance. And this is the unit cell of cobalt oxide, and this cobalt oxide material will have a unit cell or two unit cells like this. But each of the material or each of the atom in the cell will have magnetic dipole moment in this direction. In this direction, all of them they are in the same direction at a temperature below Tc. Therefore, the crystal structure is more important to give different types of magnetic materials. In one such case of ferromagnetic materials, the adjacent atoms in the lattice unit cell, they will have dipole moments or magnetic spins or magnetic dipole moments aligned in the same direction. So, and another important aspect of ferromagnetic substance is that they show spontaneous magnetization only below a temperature called Tc, where Tc is called Curie temperature and C is called Curie constant. Soon we will derive this equation. This is called Curie-Weiss law. So we'll derive this equation. Therefore, what actually happens is that above Curie temperature, these spins which are oriented in the same direction like this, okay, this is the orientation T less than Tc. If I increase the temperature, these aligned ones get randomized and they'll go in different directions. Therefore, T, when it is increased beyond Tc, they lose ferromagnetic nature and they become paramagnetic. But the most important aspect of a ferromagnetic material, of course, not only that, any magnetic material is hysteresis curve. That means how a magnetic material responds to applied magnetic field and its reversal. You know that a material can be magnetized or demagnetized by various methods. Can any one of you type in the chat what are the various methods of magnetizing a given material? And what are the different methods to demagnetize a material? Can you magnetize and demagnetize materials? I know you at least equipped with some of the techniques to magnetize and demagnetize. So type different techniques how to magnetize and demagnetize the materials. What are the one Anaga has posted that external electric field or magnetic fields. Yes, that is correct. And Sheikh Arif is also correct. Rubbing a magnetic material with another permanent magnet in the same direction, if you rub it many times, it becomes a magnet. And by electromagnetic induction also you can make a material magnetized. So now I will show a curve here how to magnetize and demagnetize a material. And the curve I am drawing here is for a ferromagnetic material. Any magnetic material you can draw the curves, but our interest is for ferromagnetic substances including ferrites and antiferromagnetic materials. So the curve drawn between the external field H and the magnetization it causes in the given sample of the magnetic material is called MH curve or BH curve. So I am now showing you the curve. I am taking magnetizing field means I can increase or decrease the applied magnetic field H. This is H, applied field. This is applied field. Okay. And when the field is applied and an external and the substance or the sample, if it is placed in the external field, it get magnetized. So that magnetization we call it as M. Once it get magnetized, it means a magnetic flux is induced in it. Therefore, on the y-axis, I can take either M or B. So this is curve is called BH curve, generally mostly known as BH curve. And from this you can define another important topic called as hysteresis of a magnetic material. Now look at this. I start at 0, I slowly increase the magnetic field and I see how the magnetization in the sample increases. So the first point is that when I look at the curve goes like this. That is, as H is increased, the magnetization is also increased and become maximum. After maximum, all the entire domains in the ferromagnetic substance are started aligned in the direction of applied field. Even though you increasing the field, there are no domains that can be turned into the direction of H. Therefore, we'll have a saturation. That means this is saturation. So with increasing H, the magnetic material can be magnetized, and as H increases, it gets slowly magnetized and gradually it becomes magnetized with a maximum value here, and then it reaches a saturation value. And further you cannot magnetize it because all the domains inside the ferromagnetic material are already aligned into the direction of the applied field. Now, once it is magnetized completely, I want to demagnetize it. Why demagnetize it? I just decrease the magnetic field from higher value, from maybe here, I slowly decrease the magnet. And we know that as the field is decreased, it follows the same curve and comes to 0 when H is 0. But surprisingly, it was found that when the applied magnetic field is gradually decreased, it will not follow the previous path when it is magnetized. This path, it will not follow. So, but which path it will follow, we have to see. Now, I am decreasing the magnetic field in the opposite direction. Slowly I am decreasing. If I decrease it, this goes like this. That means it is not following the same path as it has followed for magnetization. So therefore, you can see that here the applied magnetization or B is not zero even the applied field is zero. That means the sample is not coming to completely demagnetized state. We started the magnetic material in demagnetized state and magnetized completely, and I want to demagnetize it. When I'm demagnetizing it, it is not following the same path. However, not only for not following the same path, it is its magnetization or magnetic field strength in the sample is not zero, even the applied field is zero. That means it is showing some residual magnetism in it. So thereby, once magnetized the sample, if you want to demagnetize it completely, and if the applied field is made zero, the sample is not coming to original state or virgin state of having no magnetism. Still, it is holding some magnetism. Therefore, if I want to demagnetize it, what I do is I go to by applying the H in the opposite direction. Therefore, minus H. This is plus H. Okay. Here is 0. I'll go. That means if I apply the magnetic field in the reverse direction, opposite direction, the curve goes like this. That means if you apply this much of negative field H, then the magnetism inside the sample will become 0. Means this much of field, negative field or in the field in the opposite direction is required to demagnetize the sample. So once again, if we increase it, it simply goes just like this as of this part. And then it get magnetized in the opposite direction because the field is negative. That means once it is magnetized with north and south poles like this, it will get magnetized with the reversal one. The one pole will be having south north. So therefore, if I want to now demagnetize it, here is we have saturation, here also we have saturation. I want to decrease the field now in this direction. If I decrease the field in this direction, you can see it will not follow the same path again, it comes here. That means even though it is magnetized in the opposite directions, okay, once I'm demagnetizing it, it is not coming to a zero B. So this point and this point are similar points, and also the 2 points which we have chosen here, that is saturation, is same as that of this point. The two are same saturated points. Now if we apply magnetic field in the opposite direction, now what happens? The curve goes like this. That means a ferromagnetic material will not follow the same path while magnetization and demagnetization. So therefore we will now say that from this curve, okay, as the magnetic field H is increasing, of course B is also increasing. As it is increasing, when it is magnetic field is decreased, it is not, the B is not coming to 0. That means there is a phase lag between applied field H and magnetization B. You studied in our other BWA classes that when a voltage is applied, the current in the circuit may lead or may lag depending on the components in it. You may have a capacitor, you may have a inductor in it, and thereby or maybe a resistor. So if the current relationship between the voltage and, okay, current that is passing through the resistance, we don't have any phase difference. But if you use inductors and capacitors, there is a phase difference between the current and the voltage, applied voltage. Here also the applied electric field, magnetic field, and the magnetization M or the magnetic flux B are, they are not following the same, means that there is a phase difference or a phase lag. The H is becoming first 0 here. In this case H is 0, but here B is not 0. So therefore there is a phase lag. Okay, so the phase lag between B and H is called hysteresis. So ferromagnetic material shows hysteresis, and any material, magnetic material that shows hysteresis is useful for memory applications. And this curve is also very important for a given material, whether that material is used to make a permanent magnet or a, or a not a permanent magnet. So that we will see about this BH curve more in the next classes. Now look at this point. So therefore, this is called saturation magnetization. This is saturated. And this is called retentivity or residual magnetism. Okay. And this residual magnetism is the magnetic field that is remaining in the magnetized sample even it is demagnetized and the external field is made zero. And this is called coercivity or coercive field, and this coercive field is the field that is required this much negative direction to demagnetize the already magnetized sample so that B is zero here. So therefore the saturation magnetization, retentivity and coercitivity are most important factors or parameters for a ferromagnetic materials, and BH curve allows us to determine the retentivity and coercivity or coercive field of a ferromagnetic materials. And this is called a BH curve or MH curve, or it's also called as hysteresis loop. So hysteresis loop or hysteresis is the process in which there is a phase lag or phase lead between H and B. But here you can see a phase lead, and this is called phase lag. This is called a hysteresis. And this is the hysteresis curve what I'm showing here, the same curve. Now, why do we have this? How a ferromagnetic material is actually having these domains and how it is showing the magnetism. That is explained by molecular field theory, which is given by a scientist called Weiss, and this is called Weiss domain theory. So according to Weiss, any ferromagnetic substance you take it, there is an internal molecular field. Internal molecular field means that in this sample, if you take, we have the areas. Within this area, we have magnetic moments aligned in one direction. This one, the magnetic moments are aligned in this direction. In this area, they may be like this. In this area, they may be something like this. Therefore, we assumed that in the ferromagnetic material, there will be at the microscopic level or atomic level, the substance contains regions in which the magnetic dipole moments are arranged parallelly. And this parallel arrangement of magnetic dipoles, which is limited to small region, is called a magnetic domain. And a ferromagnetic substance will have large number of ferromagnetic domains, and all these ferromagnetic domains are not arranged in the same direction, so the net magnetization is zero. Therefore a ferromagnetic material like iron will not show net magnetization, but it can be magnetized by applying a external magnetic field. So the regions are most important, but these regions are separated by walls which are called as domain walls. So if I take domain walls, that this is the magnetic material I am taking. Here the spins are like this, and next the spins are like this, and next the spins are like this, and I suppose say the next the spins or something in the other direction. So when they are in different directions like this, then what I do is that if I move from here to the here, all are in the same direction, these are in the same direction, this is the direction. So if I just step out from this region, first region, and move in this direction, all these are like this in the same direction. but this region is in this direction. And these two are separated by a boundary, and this boundary is called as domain wall. This is the domain wall. This is the domain. This is another domain. So we have domains separated by domain walls, and therefore there are two different techniques to magnetize a ferromagnetic material by external field, which we call it as the motion of domains or growing of magnetic dipoles in a special in an area, and also the motion of magnetic domain walls. And these two are important for giving the ferromagnetic nature when external field is applied. Now look at this. Domains are randomly arranged when no h is no or no, okay, h is equal to 0. And if I apply some h in this direction, okay, you can see that all of them are moving in the same direction of h or b, because you know that b is equal to, we have written in the last class, mu naught times okay, h plus m. If I write h plus m, you can show that, okay, this is b is proportional to h, or more the h, more the magnetization. Therefore, I can take here b value. Hence, we'll say that the domains may be randomly arranged when there is no field, and they are got arranged in the same direction. So, this what actually happens. The regions will show spontaneous magnetization, where the spontaneous magnetization and domains are oriented in the same directions. Okay, they show net effective magnetization limited to this area. This area we have magnetization. This area we have magnetization. This area also we have magnetization. But they are in different directions. So net will be 0. But coming to here, because of applied field, all of them aligned in the direction. So the dipoles are in the same direction, hence we have magnetic properties. Sure. This is will happen only below Tc. If you go for a temperature more than Tc, thermal agitation makes the magnetic dipoles to get random, and therefore it will lose its magnetic property, ferromagnetic property, and behaves as a paramagnetic property. Now look at this BH curve. This is the BH curve which we have explained earlier. This BH curve, how to explain? By using domains. Initially, I have started here. When it has started here, the material is in not magnetized condition. The whole material is not magnetized, but inside the materials, domains are magnetized, but they are randomly oriented. If I take here, the case will be like this. Okay, like this means that they are randomly oriented. As I am increasing the h value like this, they start moving in the same direction of h. This starts tilting like this, or reorienting itself. This also reorient, and this also reorient, and this also reorient, and the magnetic field start reorient. And as the field is increasing, more and more domains start aligning themselves in the direction of applied field by rotation. As they are rotating, the magnetization, or B, inside the sample increases. Once saturation is reached, all those domains which are randomly distributed now are in the same direction of applied field. This is the applied field direction. All of them are in the same direction. Therefore, the magnetic material is completely magnetized, and all the domains are rotated and aligned in the direction of applied field. Hence, we say that, okay, the material gets magnetized. Now, when I demagnetize it, means that I am just going back. When the field is decreased, up to this, the saturation is okay. After saturation, as the magnetic field is decreasing, these already aligned magnetic dipoles start moving in different directions, like this. Some of them like this, some of them are like this. When you're increasing, okay, And at this point, when H is 0, all of the domains will not be coming back to their original position like this. Some of them are still in the same direction, and few of them only get disturbed and they come like this. Therefore, majority of the sample is having magnetization in some specific direction, and so only few regions are in the opposite direction. Therefore, this is majority compared to this, and a net magnetization is not zero. Therefore, the substance retains some magnetism in it, which is called as residual magnetism, and it is called retentivity. So is retentivity at a point this, I say this is 0, A point, and of course if I take point okay, B here, in point B, not all the domains are in the direction of applied field. Few of them are in different direction, but majority of them in the same direction. Therefore, B is not 0. If I'm applying now the magnetic field in opposite direction, negative direction like this, again they get demagnetized. And slowly these also, which are there here, also get randomized. And once they get randomized at a field equal to Hc, this is Hc, we call it as, all of them will be in different directions, making the net field 0. Therefore, B is 0 here, which is similar to this case. Both cases are same here. And if I increase the field again, which are there in this direction, they start moving in opposite direction because the field is in opposite direction. All of them try to align, and therefore at this saturation point, all of them are in the direction of applied field. This is the applied field direction H, and within the field, this is also H direction. This is the B, of course, they are in the direction. And if I again change the direction of the magnetic field, they get demagnetized and will get the same point as of this. And again, if I increase the field, they get demagnetized, they get randomized. Likewise, we can say that the hysteresis, in the hysteresis curve, initially domains are in random directions. As H is increased, they start aligning in the direction of applied magnetic field. Once the applied magnetic field is sufficiently large, all the domains will be in the same direction of applied field, and you will get a saturation magnetization. If you decrease slowly, then already aligned magnetic domains start rotating in different directions, and therefore, if the magnetizing force is 0, some of the materials will, some domains will be still in the direction because they are not able to orient themselves completely in random direction. Therefore, a residual magnetism will be there. If you apply magnetic field in the reverse direction, then they get completely randomized, and a randomized one makes the sample in go to non-magnetic state. Therefore, B is equal to 0. This is why you can see that there is a lag of B with respect to applied field H. This lagging of magnetic field induction B inside the material due to applied magnetic magnetization force H is called hysteresis. So therefore, hysteresis will tell that there is a residual magnetism, and you need to apply an opposite field to demagnetize a given material. And Weiss molecular field theory. And this molecular field theory we will see in the next class. And if you have any doubts, you can ask me. I stop here, and those who are having doubts on this, they can give their raise their doubts in the chat.